When looking at the prefix chart that you see up here on the board, you can take a look and determine the words, meanings of different words based off of the prefix. And the prefixes that you see here of tri, quadra, penta, hexa, hepta, oct, nona, and dec are all numerical prefixes for certain words. Okay, for example, a triplet is one of 3 children born at birth. So how many children are in a quadruplet? Okay, there are 4. A quadrennial is something that happens once every 4 years. Okay, something like the Olympics. What would an octennial, how often would an octennial happen? Okay, once every 8. Decathlon. Okay, decathlon is an athletic contest that consists of 10 events for each participant. Okay, and the winner of the decathlon in the Olympics is considered the greatest athlete in the world. What would a pentathlon have? Okay, pentathlons have 5 events. And then what about a heptathlon? Okay, a heptathlon would have 7. Hexapods have 6 legs or feet. A tripod would have how many? Okay, 3. An octogenarian, a person between 80 and 90 years old. So a nonagenarian would be between 90 and 100. A pentagram is a 5-pointed star, so a hexagram would be a 6-pointed star. An octahedron is a solid geometric figure with 8 plane faces, so a decahedron would have how many plane faces? Okay, 10. An nonagon is a polygon with 9 sides and 9 angles, so a heptagon would have how many? Okay, 7. A heptameter is a line of verse consisting of 7 metrical feet, so a pentameter would have 5. Okay, so those prefixes are going to become important as we take a look at naming polygons. And we're going to focus on a couple different pieces today as we go through our polygon section. And a polygon is a plane figure that meets the following conditions. It is formed by 3 or more segments called sides, such that no 2 sides with a common endpoint are collinear, and each side intersects exactly 2 other sides, one at each endpoint. Okay, and at this point we'll pause the presentation and let you get those definitions down. Each endpoint of a side is called a vertex of the polygon. A polygon is considered convex if no line it contains a side of the polygon contains a point in the interior, and a polygon that's not convex is called non-convex or concave. And that'll be our main focus as we go through our lesson today, is whether a figure is concave or convex. And polygons are equilateral if all of its sides are congruent. And again, we'll pause the presentation at this point to get those copied down. Polygons are equiangular if all of the interior angles are congruent. A polygon is regular if it's both equilateral and equiangular. A diagonal of a polygon is a segment that joins 2 non-consecutive vertices. And finally, our first theorem from this unit, the sum of the measures of the interior angles of a quadrilateral is 360 degrees. Just like we had an interior angle sum, or a triangle interior angles theorem, where their triangles add up to 180 degrees, we have it with quadrilaterals also that they add up to 360. And again, we'll pause the presentation at this point. Okay, so we take a look at our polygons, and we take a look at the way that they are named, and we use those ideas of the prefixes we had on our very first slide. And a 3-sided figure within a polygon is a triangle. Okay, you guys have learned about those from the time that you were little. Okay, but a triangle is a 3-sided polygon. Okay, what about a 4-sided polygon? And you've got to make sure that you're very generic with this one, but a 4-sided figure is called a quadrilateral. Okay, I know that there's probably a lot of different answers out there. There's squares and rectangles and all those, but those all go into the subcategory of quadrilaterals. What about a 5-sided figure? Okay, the biggest one you all saw when you went to Washington, D.C., a pentagon. What about a 6-sided figure? Okay, a 6-sided figure is a hexagon. What about a 7-sided figure? Okay, heptagon. An 8-sided figure. And hopefully you all know this. If you don't, you should hear in the next year or so when you start driving, but that is an octagon, just like your stop signs. A 9-sided figure would be a nonagon. And a 10-sided figure would be a decagon. Okay, so at the bottom of the front page of the notes, we're going to take a look at the different shapes that we've got, and we want to identify the types of figures we have. So number one is obviously a triangle. Okay, number two, okay, we got a pentagon for that one. What about number three? Okay, there's 6 sides there, so that one's a hexagon. Number four. Okay, 4 is the octagon. Okay, it is the stop sign. Number five. Now, number five, you could have probably a lot of different choices with this one. We're going to go very generic again with it. We're going to go with quadrilateral. It looks like it might be a rhombus, but we're not 100% certain. And number six. Okay, it's a decagon. There's 10 sides. Any questions or no's? Okay, so the naming of the figures is going to be a piece of this, and one of the things that you're going to be asked to do is determine whether or not your figure is concave or convex. And you're going to be able to use the diagonal to tell if a polygon is concave or convex. If all the diagonals of a polygon lie within the polygon's convex. And if it's not convex, it's concave. Okay, and you can see here our diagonal from V to Y, okay, which I'm going to highlight here in yellow, passes outside of our shape. And that tells you that the figure is a concave figure. Now, remember with our figures, one of the key pieces to this is with a polygon, all the pieces have to be made up entirely of segments, and you only have 2 segments meeting at a point, and it has to be enclosed. Okay, so we want to tell whether our figure is concave or convex. Okay, and if we take a look at number 1, it is possible to draw my diagonal from L to J outside of my figure. As a result, that figure is concave. Then we've got to count our sides to figure out how many sides we have in that, and that is a concave hexagon. Okay, number 2. Every diagonal that I draw from M stays entirely within my shape. It cannot pass outside. As a result, I know that that figure is convex. Count my sides. There's 8 sides there, so that's a convex octagon. Okay, questions on those? And while those marks are there, they're only there to count tallies. They don't actually mean that those segments are congruent. Okay, what about this one on number 1? Okay, again, here's a diagonal, shaded there in blue. So my figure is concave, and that is a hexagon. There are 6 sides. And number 2 is also a hexagon, but this one is actually convex. Okay, because again, trying to draw my diagonals, all of my diagonals stay within my figure. Now, just as a highlight for what we're going to be continuing to look at, as you look at what's up here on the board right now, you'll notice that I drew 4 triangles within that hexagon. That's going to become a key for what we're going to look at tomorrow when we take a look at our interior angle sums of convex figures. Our next example, okay, is it concave or convex? Okay, again, I can draw my diagonal. This one passes outside. So my figure is concave, and if I count my sides, okay, it's a concave nonagon. There's 9 sides to that. What about letter A? Okay, again, diagonal can pass outside, so this is a concave. And if you count your sides, there are 4. It's a concave quadrilateral. And over here for letter B, there are 6 sides, so that's a hexagon. And again, if I were to draw my diagonals, you notice that my diagonals cannot pass outside of my shape, so that is a convex hexagon. Any questions so far? Okay, again, counting our sides, we've got a pentagon. There are 5 sides on this one. Okay, and again, my diagonal will pass outside, so that is an example of a concave pentagon. Okay, over here with number 2, there's my diagonals. Okay, and if I count my sides, 2, 3, 4, 5, 6, 7. have a convex heptagon. Any questions or no's? So basically, when you're looking at something that's concave or convex, one of the big keys is that you're going to have an open space, whether it's a notch in or a notch out. Now, the other part to what we're going to look at today, before we get into the quadrilateral sum theorem, is whether our figures are equilateral, equiangular, or neither. So now the markings on our sides are going to matter. We take a look at number 3. Okay, are all the sides marked off the same? Okay, yes, we have that. Are any of the angles marked off the same? Since there's not, that tells us that our figure is equilateral. Because we don't know that it's equiangular, it cannot be regular. Okay, on number 4, are all the sides marked off the same? Okay, the answer to that's no. And if you look at your angles, you'll see these two angles here are marked with 1. That angle on the right is 2. The angle on the left is 3. So that is neither equilateral nor equiangular, because none of the sides, or all the sides are not marked off the same, and all the angles are not marked off the same. Okay, what about letter A? Are all the sides marked off the same? Nope. Are all the angles? That's also no. So that's neither equilateral or equiangular. What about letter B? Are all the sides marked off the same? Yes. Are all the angles the same? The answer to that one is yes also. So this is a regular figure. And letter C. Are all the sides marked off the same? They are, but our angles are not. So that is simply an equilateral figure. Okay, taking a look at the picture on our right-hand side, is our figure regular? Okay, our answer to this question is yes. Okay, it is both equilateral and it's equiangular. Okay, we're going to draw an equilateral quadrilateral that's not regular. Okay, your best example here is to try to draw a rhombus. Mark off all your sides the same. Don't make sure that you don't mark any of your angles equal either. The regular quadrilateral is going to be a square. We want to make sure that we avoid drawing that. But an equilateral quadrilateral is a rhombus where all the sides are the same, but the angles are not. Okay. And our last two slides are going to deal with the quadrilateral angle sum theorem. Okay, and the quadrilaterals always add up to 360. Okay, our quadrilaterals add up to 360 on the interior angle if it's convex. All right, so when we take a look at the picture we've got here, I have angles D and C. Okay, so these two angles down here are both 90 degrees, so that's 180. So I'm going to take 360 minus 180. Okay, that gives me 180, and that leaves me angles A and B combined. Now what I'm going to do is subtract 67 away from that, and 113 equals the measure of angle A. Okay, so I'm simply subtracting away from 360 degrees. Now, if you're given values of x's instead, you're simply going to add those pieces all together and let them equal 360. So I'm going to take, for this problem, 8x, 2x plus 13, 153, and 3x minus 1, and let that equal 360. My number of x's is 13. 13 plus 153 is 166. When I subtract 1 away, I get 165, and that's going to equal 360. We'll subtract our 165 from both sides, which means that 13x is 195. And if I divide both sides by 13, I should end up with x being a value of 15. So the angles in a quadrilateral add up to 360, just like the angles in a triangle add up to 180. Okay, and at this point, if there's no questions, we'll go ahead and pause the presentation and pass out the homework for tonight.